Hello and welcome to the second video in this new StackIt series. Last time we did work on just having AI look over our repository, find any bugs, improve the front end. So now we actually have a good looking front end. And in this session, I actually want to get started with the AlphaZero idea. So back when I did the first YouTube series, I already implemented Monte Carlo Tree Search because, as far as I remember, AlphaZero uses this together with a neural network that judges the board position. I think it's two networks. One of them actually tries to predict the best move, I think, and the other one just predicts who will win given that board situation. I want now AI to do this for me, so I think we will just instruct it to read up on how AlphaZero works, and then we let it run for a little bit and try to implement some self-play learning mechanism. For this I will use voice mode, and then while the AI is running we will pause the video. Hey Opus, I want to implement something that is similar to AlphaZero in this repository. I want some neural network that plays itself and just gets really good at the game. In order to do this, I want you to search the internet and read some Medium posts and tutorials on how AlphaZero works. If you can find the original paper, that's also something that you can read, and then come up with a plan on how we implement this locally. Ideally, while the training is running, you give me a small UI that lets me visually see how training is going. This would be nice, so I have something to show. But first, read up on all the information and then let me know how we implement this. Okay, and while Opus is now going out and studying my codebase, I will pause the video and we will be right back when the review from Opus finishes. I just quickly want to come back for people who might not be so familiar with the Claude code harness. So the code base reading finished, but the agent told me it's still waiting for the research agent to finish. And if you press the down button, you can see this is the main agent, or I can go to the general purpose research agent, and if I click this, I can see what this agent is doing. Now this one is actually finishing up, I guess, but you can see up here it did like web search, it fetched some pages, it fetched some GitHub repositories, and then it came up with this is the response essentially. It said this is how the training loop works, this is pseudocode, this is how the formulas all work out, neural network architecture, small network. So it feeds all of this, including the hyperparameters, back to the main agent, including all of its sources. And now if I go back, actually we can see the AlphaZero agent finished, and now the main agent is synthesizing the information it got from the sub-agent. So it had one agent that checked the code base, and it had one agent that checked the AlphaZero implementation. And okay, it immediately finished too. Here's the plan. AlphaZero policy iteration guided as a neural net generates self-play games. The net trains to imitate the search, improve policy, and predict the winner. Repeat. No human data, no handcrafted eval. Yes. Torches there. MPS. I'm on Apple. Is good. No new dependencies. StackIt is a great fit because yeah, that's why I chose this game. It has a tiny action space, so I can actually probably train something on my local. Encoding, board to tensor. My turn. After any move resolves, counts are always 0 to 4. 9 binary planes. Okay. Just to give some explanation, the input layer of this network will have 9 times the board essentially, and each one will have a binary field on whether this particular position on the board has a stack or not. and it will have one plane for, okay, this is all the stacks of size 1, all the stacks of size 2, 3, and 4, and then it does this for me and for the opponent, and then the empty board, or which spots are still empty, and then it will augment this. So, you know, we can rotate the board, we can flip it. Okay, small residual tower. 2 heads, policy, self-play training, each iteration plays G games. I mean, this is how the network will be, right? We have residual blocks, 64 filters, 2 head, one is the policy head, and one is the value head. This is essentially what I said earlier. The policy head will give us which move should we take, and the value head will say how good is this board position for us. Then we do these MCTS rollouts according to this formula with certain parameters that I got from all the research. Self-play and training, evaluation, engine wrapper, live dashboard. Okay, build order, encoding, self-play, live dashboard, wire it up, wall clock, single-threaded batch. Per iteration, learning should show within an evening. I don't want to wait an evening. We have to speed this up, but first let's get it implemented. Near, fastest possible sandy chain. I usually think training on smaller examples is better, because we don't want the computer to spend a lot of time really training something yet. We just want to make sure the code is correct, and scaling it up should be possible. What is it asking here? How rich should the live curves plus live set? A bit more work. Yeah, okay. This one is good. Now good, let's go with the recommendation. I think even a 4x4 board should not take that long to train. It now says single threaded. You know, for AI it's actually trivial to multi-thread this, I think. And we should just make sure that the MPS interface is busy. Here I will pause the video again, and I will be back when Claude is done cooking. Okay, welcome back. As you can see, the dashboard has a similar UI design to our game. It's running. We're gonna look closer at it in a second. First, I want to go back into this terminal. We can see Claude has been running. Does it show? Here it says 1 minute, but before that it was running for 15 minutes or so, and it has been doing a lot of stuff. I don't want to look into everything in detail, but I just want to show you, you know, while waiting, you can see it's writing all of these code files. Yeah, here we approved the plan. Then it started writing a config, some encoding, some neural network code. And then it performance tested the implementation already. Evaluation harness, self-play, writing the loop. Here it was actually testing whether MPS or CPU is faster. And somehow it said that MCTS, since this is running sequential, CPU is actually faster in its benchmarks. But it talks about batched training. So I guess it will run multiple games in parallel and then batch the training. We can confirm this later. The UI, dashboard, okay, and then it was implementing a bunch more stuff. Apparently we have integration tests, readme, and then here it was started, you know, running some iterations and checking the performance to see if it actually works. And then here it gives me the, okay, I'm done. I'm not sure which metric it is giving me here. This is also something we have to ask it. Live dashboard, core pipeline, we have the encoding, which encodes the board. Okay, the net, MCTS, train, arena, counts are always 0, 4 post moves, so 9 binary planes are exhaustive, illegal move masking and value sign flipping isolated unit tested. Okay. How to use it. Validation run is just 6 small iterations. Stop it and launch for the real thing. Honest expectation. Beating random happens fast already there. Closing on your AlphaBeta takes many iterations. Plan on an evening, 50 to 80. Once 4x4 clearly beats AlphaBeta, bump board to 5. Want me to let the validation run finish and show you the trend or stop? Now I want to look at it a little bit. So here's the, currently apparently we are on iteration 4. We have a 95 win rate versus random, but 0 versus our AlphaBeta. You know, there's a lot of things we don't know, like how is it playing against AlphaBeta? Is it actually, is it running with a time limit? Like what's the time limit? 1 second, 10 seconds, or whatever. So, you know, there's a lot of things that are not clear here. Random gate candidate versus best. It's the win rate. So maybe the numbers it was telling me about is the win rate. And this is the training loss for the policy net and the value net. Yeah, it still looks... Oh, what happened here? Let's see if these games make sense somehow. It fills them. And then it's kicked it over and suddenly the whole field is yellow. It looks a little bit buggy, but depending on where the 4s are. This game looks noticeably different, so the win rate. Candidate versus best. Yeah. Network plays itself, learns from Monte Carlo Search, and hopefully climbs live from checkpoints. Okay. I will leave this running a little bit while I ask Claude some questions. Okay, I think we should let it run. Can you tell me, the numbers you're reporting up there is win rate, right? So iteration 1 had a win rate of 0.42 versus the iteration 0, I guess, and iteration 2 had 0.7. Or is this the loss? And also win versus random, you said it went from 0.85 to 0.9. That's like the win rate, right? When you play against AlphaBeta, how do you measure this? Is there a time limit? If so, how long is AlphaBeta allowed to think? And I mean, I guess our network as well. And just because I'm not so familiar with the paper anymore, can you tell me a little bit more about how the gate phase and the benchmark phase are working and how the training in general is working? I understand the network is playing against itself, and in between we are training. And you mentioned CPU versus batch training. I guess this means how many games we play on one version of the network before we train. Just give me a little bit more details about all of this. Okay, I will pause here and come back when it's done, and or I have some updates in the training. Okay, this time it was rather quick. We have a long answer. Let's quickly look through it. Everything up there is a win rate, not a loss. Okay, wins plus half the draws divided by games played. The loss numbers are separate. The gate, how often the freshly trained net beat the previous net, tier 1. New net beat the old one only 40% of the time, rejected. Iteration 2, 70% accepted. Okay, yeah. Versus random win rate. Okay, how AlphaBeta is measured. It gets 0.05 seconds of thinking time per move. Our net is not on a clock in these matches. It does a fixed 40 MCTS simulations per move. Okay, yeah. Regardless of time. So how the two are roughly matched in a wall clock but capped differently. AlphaBeta by time, our net by simulation count. Okay. One iteration. Wait, how much did we say does it do? 40. Yeah. Okay. In 4 phases, self-play. The net generates its own training data. Current best net plays 10 full games against itself. Okay, on every move it runs 40 look-ahead simulations guided by the net. It records 3 things per move: the board, the visit distribution, and who has to move. Example, on some boards spend 25 of it 40 simulations on this move. That board gets labeled policy mostly when the game ends. Say player 1-1. Every board where player 1 was to move gets labeled as value +1. Ah yeah, okay. Training, fit the net to the data. All those labeled boards go into a replay buffer. Yes. We take 200 mini batches and nudge the net's weight so the policy output matches MCTS visit distribution and its value output matches who actually won. Okay. So the net learns to predict what the expensive search would do next iteration. Its raw guesses are better, so the search is better. Yo! Which is 10. Okay, how many games before we train 10? 40 by default. Okay, play 10 games, train, repeat. Gate phase. Is the new net better? Okay. Okay, interesting. So I just want to show here in these phases, I saw gate and benchmark, and now we are actually in phase done. I think this is because it said we only run 6 iterations. Maybe, yeah. One thing we notice here is why does it not topple this over immediately, right? And now this one should topple, and like orange should have prevented blue from doing this. So it's not very good yet. But one thing we can actually see, we have a 5% win rate versus AlphaBeta already, so it seems to be learning something. Let's quickly learn about these phases. After training, we have a candidate net and the previous best net. Then they play 30 games head-to-head, color swapped each game, no randomness. Okay, if the candidate wins more than 55% of the time, it becomes a new best. Otherwise, we throw the training away and keep the old weights. Ooh, I thought we might just keep training, but one bad training update could make self-play generate garbage data. Okay, the gate is a safety check. Okay. Okay, benchmark phase. How good are we? Absolutely. Gate only tells us better than last time, while both nets are weak. So we play the net versus random and versus AlphaBeta purely to log a number. This doesn't affect training at all. Okay, it's the benchmark phase. It's not about game counts, it's purely which chip runs the math. Ah yeah. Self-play asks the net about one board at a time. Batch of 1. Ah yeah, okay. Okay. Yeah, I could have told him that running the prediction on MPS is probably not fast enough. Okay, that's very good. I think the 6 iteration simulation that you left running is done now, at least according to the UI. And we ended up winning 5% of the time versus AlphaBeta and 85% of the time versus random, which is not too bad, I think. Now my question to you is, before we run the larger training that we run maybe for a couple of hours, should we do another check on optimizations? Like, where are we actually spending most of our time? Should and can we optimize something here? I also don't mind doing the self-play in parallel. We can probably run all 10 games in parallel since it's on the CPU, which probably speeds this part up. Just a question. If you think we should just run the full simulation or the full training right now, then I would ask you to spawn it in the background and make sure that the dashboard picks up the new checkpoints so I can monitor it. Okay, yeah, sorry, I was just looking at the dashboard over here. Can we add the, yeah, I will just queue this up and pause the recording until we get the next output, and I guess then we monitor the main training a little bit. I might then pause the video for a long time and just let it run for an hour or two and see how far it gets, and then just show you the result of this. Yeah, that's how I'm gonna do it. Okay, we are back. Claude did some profiling and said that self-play only makes up 15% of each iteration, while the evaluation, gating and benchmarking makes up 85%. I mean, I can imagine this because in the self-play we don't have a time constraint. We are just moving as fast as possible, while over here we have these, was it 0.5 seconds or 5 seconds per move for AlphaBeta. But nevertheless, parallelizing all gameplay makes it faster, right? So we also run these evaluation games in parallel. From 28 seconds per iteration down to 28 per iteration down from 135. So 5x improvement, which is already good. So now it takes 90 minutes instead of an evening. That's what I want. I don't want to spend my evening waiting for this. The training is running. In the background, restarted. So it's iteration. It's a fresh run. So the curves start from iteration 1. Is it? It's just that fast, I guess. Look at this. It already ran. Maybe I should ask it to put a timer here too, since when this is running, but yeah, benchmarking phase. The loss doesn't seem to move that much, to be honest. I wonder if we can get some legend when hovering here. That would be nice. Self-play gate, candidate versus best. So the last candidate versus best. This one was accepted then. This is also something we could improve. While this is running, let us ask it to make the dashboard better. Okay, what do we want? We want to... is there a way to add to the dashboard 2 counters? One is the time since the training started, and one would be the average iteration speed. And then, if possible, can we make the plots hoverable so that I can get some legend to pop up when I hover it to see the actual values. Also, in the win rate plot, maybe we can make vertical lines whenever a new candidate was accepted. No, that gets too noisy. I wonder if we can, or maybe underneath the latest self-play game, we can have a list of gates and benchmark, essentially a table that shows the model version and then whether it was accepted or rejected, and some parameters around the model. Around the model? Parameters of the model now. Performance maybe. Okay. In the meantime, this is really fast, and I mean, look at this. This was a really good, much better network here. I wonder if it's normal that loss is not moving very much, but I guess initially it's still a lot of randomness. And I mean, we have to, this line here is always relative to the previous version, right? So, you know, here the model got much better than the previous version, and now the next model is worse than this version, but maybe not worse than this version. So I'm not sure if we can rank it easily, but maybe I can also ask it to come up with some sort of ELO ranking between the individual models. And instead of just benchmarking versus random in AlphaBeta, we should always benchmark against a couple previous versions. Let me immediately queue this up. In the win rate plot, we always see each point is relative to the previous point, right? So if one model won 80% of the time against the previous model and the next model lost 55% of the time against the middle model, that doesn't necessarily mean that the latest model is worse than the first model, because it might just be worse than the second model, which was much better than the first model, something like this. And you know, from the chart, this is really hard to see. So I already asked you for the table with the model, and I wonder if while training it and while doing the benchmarking, it is possible to assign some sort of ELO value for the current model and previous versions. And I also thought maybe in the benchmarking stage we should not only play against random in AlphaBeta, maybe we should always also play 3-4 games against previous versions, not just the one previous version but multiple previous versions. This could then update all the ELO values. Oh good, ILO. Did it also screw up the first ELO? Can't see it. First model worst in so, table while doing. Oh no, what to do? This might only make training insignificantly slower. I mean, we have to test it, but this could actually be really nice visually to see how models evolve in their ELO over time. Okay. Claude is running. Whoa! Look at this. So here we took off from, I didn't even notice, but from iteration 3 to now 16, we have a win rate of 80% over AlphaBeta. Now we are at 63 with the latest version, but I guess we rejected this version and we are still on this one. Interesting. Interesting. So the network got really good. One other improvement to the dashboard would be that we stop showing the self-play and we actually play against the current best model candidate. Yo. Nice. Okay. I think we are almost at the end of this video. I will still, I can't stop, but I will still let it add all of these improvements to the dashboard and then show you the dashboard, and I think then we're gonna wrap it up for today. Okay, actually I forgot to unpause, but the last thing we did, I think I asked it to implement these ELO ratings, and it did. And it tells me about the new ELO system, how everything plays against each other, and then I actually, you know, once the ideas start flowing, it's really hard to stop. I thought it would be nice if inside of this UI, the new UI, we can actually hit a play button and then we play against the latest best version at that particular point in time. And ideally that best version would also output search statistics, like out of the searches that it did, this is the number of times it won the game, and this is the best sequence of moves how that it found, ideally for both players. I'm not sure if Monte Carlo Tree Search gives us this, but something I want to add here is also, yeah, I mean, okay, value head is essentially one thing I mentioned already. But here we have the ELO version. Let's quickly look at it. I said, okay, I want training times. It added this. The best ELO is actually this particular model. Ah, yeah, okay, this is really nice. Okay. Self-play phase, ELO rating of our best model is increasing. Training loss. Okay, this is everything we need. Here you can see which is the currently best version. Version 0, I'm not sure if version 0 can actually be rejected. I mean, okay, I guess this number is random because version 0 plays against version 0 and one side won 55% of the time. That's the accepted one. Version 1 already improved. Version 3 got rejected. Version 4 got accepted. Version 5 got accepted. I feel it's a little bit hard to see which version is currently the best. No, isn't it? Is this the currently best version? This is the version that trained now. No, version 4 is accepted. Yeah, anyway. I wonder if we should also add Minimax into the mix. yeah, the ELO ratings are converging. But still, I'm excited to see the self-play version. I kind of want to show this to you too. So this time really the last pause. Okay, we are back. We have the self-play, and now we have the play the best button, where, you know, I can just start playing somewhere. And AlphaZero, I shouldn't call it AlphaZero, algorithm will run for 5 seconds, and it roughly simulates 3000 moves. And we can see this, the policy head. I have to actually ask how to interpret these numbers. I would assume higher is better. But let's just play a couple moves and see what it thinks. Yeah, so now this one was the clear winner. And now I have to do this, otherwise it can topple over and dominate me. Now I'm gonna set a trap. I wanted to topple this one over because now I'm gonna dominate it. Ha, it didn't. Oh, because if I topple this over, this will become a 4. Ah, smart. Oh, what am I gonna do here? It thinks it's winning decisively. Seems I screwed up already. It's a little bit, the policy head is interesting to me because it shows that, this is the number of times it searched here. No, cannot be. We have 2000. Nobody wants to be the first one to topple. And I think I need to be the one. No. Oh god, that's how it's winning. Na gut. As you can see, superhuman performance. That's gonna wrap it up for today. I will think about what I would want to improve here. And maybe make a third video out of it, or maybe that's already the last video in this series, and next time we're gonna go to one other project that I have where I wanted to do some deep reinforcement learning. Thank you very much for maybe watching it, and if you have any recommendations, feel free to comment down below.